Okay, in the previous classes, we have discussed about discrete Fourier transform DFT. Okay, so we've seen that DFT is obtained by sampling the frequency spectrum and the frequency domain. That is, if you have a sequence xn, if you find its discrete time Fourier transform, you get x omega, and then if you sample it, if you take the samples of DTFT, you get x of k, which is called as discrete Fourier transform. And if you apply inverse DFT, you can recover the original samples from the samples of frequency spectrum. Okay, and moreover, we have developed a relation in which you can directly obtain x omega from xk, that is samples of spectrum. Okay, so we have got two equations, one for DFT, which was xk is equal to summation of x of n wn to the power kn, and the second equation for IDFT, this is for DFT, and for IDFT we have 1 by n summation of xk wn to the power minus kn, where k is from 0 to n minus 1. Okay, and wn is called as phase factor or total factor. It is defined as e raised to power minus j 2 pi by n. Okay, this is what we have discussed, and then we have discussed how you can compute DFT using the linear transformation. Okay, now we will study important property of DFT, that is circular convolution. Okay, and you will see that how it is different from the linear convolution that you already know. So before discussing the circular convolution, we will discuss the circular shift of a sequence. Okay, and to understand this, we start from a sequence, suppose xn. Let us suppose I take a sequence in time domain, and n is equal to 0, it is 1, then 2, then 3, and then 4. A finite discrete time sequence I have taken. Okay, when you take it to DFT and then you apply IDFT, you have seen that in the IDFT what you can recover is a periodic sequence, which is the repetition of the same sequence after n samples. So if you take it 4-point DFT, from the 4-point DFT, when you apply IDFT, you can get a sequence like this. Okay, which is called as XPN. So it is 1, 2, 3, 4, then 1, 2, 3, 4. So this sequence repeats after 4 samples. Okay, and if I delay this sequence in time by some samples, suppose 2 samples, it means if I plot xp of n minus 2, so what I will get? So since it is periodic, so 0 at minus 1, it will be again 4, then 3, then 2, then 1, and so on. So if I shift this sequence by 2, the periodic sequence, at 0, you will get 3, then at 1 you will get 4. Okay, and so on. And then 1, and then 2, then again 3, 4, and so on. So at n is equal to 0, we are getting 3, then 4, then 1, then 2. Okay. And if I just take its first 4 samples, that is at 0, 3, then 4, 1, and 2. Okay. This I suppose write as x dash n. And you will see the relation between the original sequence and this shifted sequence. Okay, this is x dash n, this is xpn, xp of n minus 2. Okay, so what I have done, I have taken a sequence of 4 samples and then I have generated a periodic sequence which is a repetition of this sequence after 4 samples. Okay, xpn, that you already know, it was summation of x of n minus ln summation over l. Okay, in fact this is what you recover from the samples of the DFT. Okay, you cannot recover directly this. From this sequence you can recover xn if you just take its first 4 samples. This is how we do. Okay, and if you shift this periodic sequence xpn in time by 2 units and then you take its 4 samples, you will get this sequence. And if you see in time, the x of n and x dash n, they are related by a circular shift. Okay, means if I plot them on a circle, 4 points, this is x0, this is x1, this is x2, and this is x3, and then I plot x dash n, that is x dash 0, this is x dash 1, 2, and 3. So x0 is 1, it is 2, it is 3, it is 4. Now it is here 3, then 4, then 1, then 2. Okay, and you can see that you can get this sequence from this sequence if you rotate it by 2 samples. Okay, if I rotate this sequence by 2 samples, so what will happen? This 1, if you rotate by 1, it will go to this point. If you rotate it by 2 units, this x0 will go here. It means 1 will come at 3. Sorry, this will become at this point. 3 will come here. This 2, this 4 will go here, and this 2 will come here. Okay, this is obtained by shifting this sequence in a circular way by 2 samples, and this sequence and this sequence, they are basically same. Okay, it means this sequence x dash n, it is related to x of n using a circular shift. Okay, in fact we relate it using a modulo operator, and we write x dash n is equal to x of n minus k modulo n. Okay, or we write it as x of n minus k mod n modulo n. Okay, for example, in the previous case you have n is equal to 4, the length of sequence, and k was 2. It means your x dash 0 will be equal to x of n is 0, k is 2, it is x of minus 2 mod 4. X of minus 2 modulo 4 is nothing but x of 2. Similarly, x dash 1 is x of minus 1 Now n minus k is 2, n is 1, n minus k is minus 1 mod 4, which is equal to x of 3. And similarly x dash 2, which is x of now 0 modulo 4, it is x of 0, and x3 will be x of 1 modulo 4, that is equal to x of 1. Okay, so 2, the sample at 2, this is xn, x0, x1, x2, x3. So 2 in x will be 0 at x dash. It means it is shifted by 2 units. Similarly 3 will be at the sample at x is equal to 3 will be the sample at x cap is equal to 1. So this is again shifted by 2 units and so on. Okay, and I hope you understand this modulo n operator. It is just like this. Suppose x mod y modulo y is defined as x minus y, x by y, the lowest integer of x by y. Okay, suppose minus 2 modulo 4, x is minus 2, y is 4, it is minus 2 minus 4 into the lowest integer of minus 2 by 4. So it is minus 2 minus 4 into, so minus 2 by 4 is minus 0.5, this is 0, 1, minus 1, so minus 0.5. Okay, the lowest integer of minus 0.5 will be minus 1. Okay, so it is to minus 1, so it is minus 2 plus 4, and that is equal to 2. So minus 2 modulo 4 is 2. This is how we define the modulo n operator. Okay, now we will use this concept in basically circular convolution, that is why I am discussing it. Okay, and similarly like when we have shift or fold operation in the linear domain, you have a shift in the circular domain which is denoted by x of minus n modulo n, which is nothing but x of n minus n basically. This is circular folding. Okay, you have original sequence x of minus n. If you circularly fold it, so folding means basically suppose I have sequence 1 2 3 4. If I fold it, I will get x of minus n modulo 4, and if you compute it, is nothing but it is folded around this axis. It means these 2 points will remain as it is, 1 and 3. This 2 will be here and this 4 will go here. Okay, this is what is circular folding. Otherwise you can say also like this, that initially when you write the sequence on the circle, we write in this direction counterclockwise. Okay, 1 2 3 and 4. So folding simply means that you write this sequence in the reverse direction. So if you write this in the reverse direction, you get 1 2 3 4. This is what is folding operation. Okay, so this is folding, and then this is shifting. So shifting, if it is x of n minus 2 modulo 4, it means you are shifting this sequence by 2 in the counterclockwise direction. If it will be x of n plus 2 modulo 4, you will get shifting the sequence in the clockwise direction. This is the difference. Okay, so in the linear it was shift to the right or shift to the left. In circular it is like this. Now we will use this in the property of circular convolution. Okay. In the linear convolution, you have a property that if yn is the linear convolution of xn and hn, then y omega is equal to x omega into h omega. This is called as the convolution property of Fourier transform. If you find the convolution of two signals in time, their frequency spectrums, they get multiplied in the frequency domain. Okay. In the circular convolution, what happens, or you can simply say in this case that yn is nothing but the inverse Fourier transform of x omega into h omega. Okay, it means you have two signals x and h. If you multiply you find their Fourier transforms x omega and h omega, and then you multiply them together, and then you find the inverse Fourier transform, you will get the original sequence yn, which is nothing but the linear convolution of the two signals. Okay, a similar property holds in the DFT. The difference is that instead of multiplying the Fourier transform, you have to multiply the DFT. Okay, it means if x of n, suppose it has a DFT xk, and h of n, its DFT is hk. If you multiply the two DFTs in the frequency domain, x of k into h of k, I get suppose y of k. And then I find the inverse discrete Fourier transform of this product, xk into hk. What will be my yn? This yn is nothing but the circular convolution of xn and hn. Okay. So if you multiply the two Fourier transforms in time, it is the linear convolution of the signals. But if you multiply the two DFTs in the frequency in time, it is the circular convolution of the two signals. Okay. And how you get this property, we will try to develop the mathematical proof for this, but this is what is the basic concept of circular convolution. Okay, the circular convolution is obtained when you find the inverse DFT of the product of two DFTs. Okay, so multiplying two signals or the two DFTs in the frequency will generate a signal in time which is equivalent to the circular convolution of the two discrete time signals. Okay, and how you get it? Suppose I take two sequences x1n, which has a DFT x1k endpoint DFT, that is n from 0 to n minus 1 x1n e raised to power minus j 2 pi k n by n. And the second sequence is x2n of length n, and the DFT of this will be x2n e raised to power minus j 2 pi k n by n. This is the DFT of first sequence, this is the DFT of second sequence, and I multiply the two DFTs together, I get a new function x3k, which is equal to x1k into x2k. Okay, and then I calculate the IDFT of x3, which is the product of the two DFTs. Suppose I write with x3 of m, which is the IDFT of x3k. So IDFT means it is 1 by n summation of k from 0 to n minus 1 x3k e raised to power j 2 pi k m by n. Okay, so I have to see that x3m will be nothing but the circular convolution of x1 and x2. So if you expand this equation, x3m, which is equal to 1 by n summation of k from 0 to n minus 1, x3k is now nothing but x1k into x2k e raised to power j 2 pi k by n. So we can further simplify it. It will become k is equal to 0 to n minus 1. In place of x1k, I can write the equation for its DFT. So it will become summation of n from 0 to n minus 1 x1n e raised to power minus j 2 pi kn by n. Then multiplied with x2k, again the DFT of this. So I write is a different notation here, variable change, that is in place of n I write l, otherwise n and n it will be confusing. So x2l e raised to power minus j 2 pi k l by n. This is for x2k, and then this entire is multiplied with e raised to power j 2 pi k m by n. Okay, this is what you get. And from these exponential factors you can take something common, and you can have some rearrangement in this equation. I can write it as, suppose first summation for n is equal to 0 to n minus 1 x1n, and second summation you can write for l from 0 to n minus 1 x2l, and then third summation for k, which is 0 to n minus 1, and then we combine all these three exponential factors together. So you can have e raised power, there is some common factor like j 2 pi k by n. This is common. What you will get inside is m minus n minus l. Okay, this is x3m, which is obtained by taking the inverse DFT of the product of two endpoint DFTs. Okay, now if you look to this sequence, this part, this sequence is in the form of, I can write it as in the form of summation of k from 0 to n minus 1 a raised to power k, where a is e raised to power j 2 pi by n m minus l minus n. Okay, except this k, all these factors I have taken as a one constant, that is a. So this entire factor is a raised to power k, and this summation will be equal to what? We have two terms here. One is for a is equal to 1, and one is for a not equal to 1. If a is equal to 1, it is simply the sum of 1 n times 1 plus 1 plus 1 n times, it will become n. And if a is not equal to 1, this will become a geometric progression, GP series, with the common ratio of a, because it's 1 then a square, a cube, and so on. So sum of n terms of a GP is 1 minus r raised to power n. R is common ratio, that is a in this case, upon 1 minus a. Okay, now when this will be 1, when a is 1, this entire sum will converge to n. If a is not equal to 1, it will be 1 minus a raised to power n upon 1 minus a. Okay, now when your a will be 1, okay, a will be 1 or a will not be equal to 1 if m minus l minus n will be a multiple of n, this factor. If I take m minus l minus n, sorry, minus small n, as a multiple of n, you can take plus minus both values. So in that case, suppose it is Pn, where P is an integer. It may be n, 2n, 3n, whatever it is. So in that case, what will happen here? Your A will become e raised to power j 2 pi by n into Pn. This n will get cancelled, and e raised to power j 2 pi is nothing but 1. Okay. It means when m minus l minus n is a multiple of capital N, A will be equal 1, and this series will converge to n simply. Okay. Otherwise, if your A is not equal to 1, it means if this is not a multiple of Pn, what will be e raised to power n? A is your e raised to power j 2 pi by n m minus l minus n. If this is not a multiple of, so this is small n, sorry. If this is also small n here. If m minus l minus n is a multiple of capital N, your A will become 1. And in that case, this sum will become capital N. If m minus l minus n is not a multiple of n, in that case, your A raised to power n will become again 1. Because if you raise this to the power n, it will be e raised to power j 2 pi by n m minus l minus n raised to the power n. So this n and n will get cancelled, and m minus l minus 1, since m, l and n all are integers, so this m minus l minus n will also be integer value. Okay, and in that case it will simply turn to 1. If it will turn to 1 in this series, so 1 minus 1, it will become 0. Okay. Okay, I hope you are getting it. So when A is equal to 1, this series will converge to capital N. And when will be A is equal to 1? When m minus l minus small n is a multiple of P. That is integer multiple of n. If it is not the case, A raised to power n will be always 1. Okay. So this series will converge to, I can write this here like this, the summation of k from 0 to n minus 1 A raised to power k will converge to n when l is equal to m minus n plus pn, otherwise 0. Okay, l minus n is equal to pn means l is equal to m minus n plus pn, or you can also write here minus in place of plus. You can also write minus here because it will be plus minus here. Okay, so it means when you open this entire series, you will see that, so this is x3 of m, so you put some value of m here, and for that value of n, then you run a series for m, then you run a series for l, then you run a series for k. Okay, and when this condition is satisfied, that l is equal to m minus n plus pn, in that case this entire summation, this one, will converge to capital N. Otherwise for all other values it is 0, so as a result this entire product will be 0. Is it? It means, and if you see this l minus m plus pn, this is nothing but you can relate it to the modulo n operation, that is I can write it as m minus n modulo n. Okay, and how it is, like suppose x of minus 1 mod 4 I have taken, it was x of 3. So minus 1 mod 4 is nothing but x, sorry, it is 3. Okay, it means minus 1 plus 4, it is 3. As simple as that. So m minus n plus pn means it is m minus n mod n, because the sequence is periodic. Okay, anyhow, whenever we are discussing about the DFT, although the signal itself is a 4-point sequence, but it will repeat after 4 samples. It is periodic sequence. Okay, so this sequence will now converge to, I have some less space here, I will write here x3m. Now it will become summation of, now this series will converge to n, this entire series, and this n and this n here, they will get cancelled. Okay, as a result, what you will get n is equal to 0 to n minus 1 x1 of n, and this you will get x2 of l, and l will be equal m minus n modulo n. Okay, so this equation is what is called as circular convolution. Okay, so this series is now eliminated because this series, Alice series, is replaced by capital N, and it will become capital N when this condition is satisfied. Otherwise it is 0. If it is 0, this entire x3m will become 0. Now when this condition is satisfied, this will become n, and this n is equal to 0 to n minus 1 x1 of n, and this summation will also be eliminated, summation of L from 0 to, because if for a particular value of L only, for a particular value of L, this condition will be satisfied. For rest of the values, this is simply 0. So as a result, this summation will not come into the picture, final equation. So you get this equation, which is called as circular convolution. Okay, so I will rewrite it. It is my x3m. It is summation of n from 0 to n minus 1 x1 of n and x2 of m minus n modulo n. So this equation we call it as circular convolution. It means if you find x3k, which is the DFT of x3m, that will be nothing but x1k multiplied with x2k. So if it is circular convolution in time, it is the multiplication of their DFTs in the frequency. If it is linear convolution, x3n, like in the previous case we have done, it is x1 of k into x2 of n minus k. This is linear convolution. In that case, your x3 of omega will be equal to x1 omega into x2 omega. This is the difference between the linear and the circular convolution. So if you find the linear convolution of two signals in time, in the frequency domain, their DTFTs are multiplied. This is discrete time Fourier transform, or you simply say Fourier transform. But in time, if you find the circular convolution, we denote it like this: x1n circular convolution of x2n. If you find the circular convolution of two signals in time, in the frequency domain, the DFTs, they are multiplied. Okay. So to find the circular convolution of two signals, you have to use this equation. So either you can find it graphically like we have done it for the linear. Otherwise, you have to first find your DFTs, then multiply them, and then calculate the inverse DFT. You will also get the circular convolution, like in the linear. If you want to find the linear convolution of two signals, you can also find their Fourier transform, multiply them together, find the inverse Fourier transform, you will get the linear convolution. Okay, so we will take some examples on this and we will compare how linear is different from the circular convolution.